So yesterday we talked about substitution reactions. There's a lot going on here. I really discourage you guys from trying to brute force memorizing everything. I want you to understand the why a lot. So we're going to focus on that primarily. And we said with substitution reactions, we have one option where the leaving group pops off first. You form a carbocation, and then your nucleophile can attack in. We said that these types of reactions go through an intermediate, and the rate determining step only involves loss of a leaving group, so it's a unimolecular reaction or a first order reaction. So this would be our SN1 example. And then option 2, we said, involves the nucleophile running into your electrophile and kicking off your leaving group all in one step. And in this case, the rate limiting step involves that attack of the nucleophile, so this is a second order reaction, and it doesn't have any intermediates. It happens all at once. So going back, we also talked about the electrophiles and the easiest way to tell the difference between an SN1 and an SN2. Yep.
So with the SN2 reaction, is it always going to change the stereocenter?
Yes, and we're going to talk about stereochemistry here in a little bit. So the question was about stereochemistry for SN2. But let's go back and talk about the electrophiles, right? So SN1, we said it goes through a more stable carbocation intermediate. So really for SN1, the most likely intermediates that you're going to have will be secondary or tertiary carbocations. Primary and methyl group carbocations are just too unstable for that reaction to be favorable. Versus down here where we have an SN2 reaction, we actually said the inverse is true, where the more accessible carbon is more likely to do SN2. So typically SN2 reactions involve primary groups or methyl groups, sometimes secondary carbons as well, but we'll talk about that kind of gray area of a secondary carbon. All right, and then we briefly finished talking about stereochemistry of SN1 reactions. So in an SN1 reaction, your leaving group pops off, and if you notice, our starting material was tetrahedral. That intermediate has what geometry now? It's sp2, so what would that shape be? Trigonal planar, right? So it's a planar molecule with a p orbital sticking up through it and down through the bottom. That means that that chloride nucleophile can attack either face of the trigonal planar geometry. However, that bottom approach we know is slightly blocked by that iodide that just left. So we said that you get two products. You get one where it's an inversion. That means that your chloride is now attached to the opposite face that your leaving group was attached to, or retention, where the new nucleophile is added to the same face that your leaving group fell off of. In this case, it was a mixture of enantiomers, but like we said, sometimes you get a mixture of diastereomers if you have other stereocenters. But let's talk about SN2 reactions. This gets a little tricky too. So SN2 reactions have their own unique stereochemistry, and so I'm going to do example A, and we'll compare this to another example. Okay, and for example A, I'm going to have this substrate where we've got a methyl group here, we've got a bromine coming off here, and then down here I'm going to have an ethyl group. So this is a secondary carbon. And I'm just going to keep this as a generic nucleophile. And for this one, I'm going to have an attack on the same face as our nucleophile, and we're going to kick off the bromine. So would this be retention or inversion if it's attacking the same face as your leaving group? Retention, right? So let's take a look at what this transition state would look like. Okay, this transition state, we'd still have this hydrogen there. We'd still have this methyl group. We'd still have this ethyl group hanging out. We'd be making a bond and breaking a bond, so I'm going to show those as dashes, right? So this nucleophile would be delta negative because it's halfway between a full negative and a new covalent bond. What about the bromine if we're breaking it off? It would also be delta negative too, right? Because when it pops off, it would be a full negative. And to show this as a transition state, we want to bracket it and then include a double dagger to say that this isn't a real thing. It's just a mental image of those bonds being halfway made and broken, right? And then the final product we said would involve a complete retention of stereochemistry where that bromine is going to be attached or sorry, the nucleophile is going to be attached to the same face that the bromine was attached to. So this would be retention of stereochemistry. All right, so let's take a look at example B. And example B is going to be pretty similar, but rather than a front face attack, we're going to have a backside attack. So our bromine's still hanging off here. We still have our ethyl group coming off. I'm going to slide this up more. And our nucleophile in this case is going to reach around all the way to the backside, hit the backside of that carbon, and then eject off our bromine. And just like before, I want to see this transition state. So for this one, our nucleophile is on the backside. That hydrogen's still a wedge. This methyl group's still a dash. Our ethyl group's sticking straight down now. And our bromine's coming off over here. And just like before, we know the bromine, when it's halfway off, has a partial negative. The nucleophile will also be partial negative. And when we show our final product, the nucleophile is going to be attached to the opposite face that the bromine was once attached to. So this would be an example of inversion. All right, the easiest way to explain example B compared to example A is it's almost like an umbrella flipping inside out, right? So when the nucleophile hits it from the opposite side, what would we call this geometry? Pretend like there's a true covalent bond between the nucleophile and the carbon and bromine. It's a geometry you haven't seen since Gen Chem.
Is it trigonal bipyramidal?
Yeah, trigonal bipyramidal. The one on top isn't exactly trigonal bipyramidal, right? All right, so now we've got to try to justify which one's more likely to occur and why. Does anybody have an idea? Between the top transition state or the bottom transition state, which one's more stable?
What's about gas reactions?
Well, let's think about it this way, right? Let's back up and think about Vesper theory. So Vesper theory says that electrons want to be as far apart from one another as possible, right? Because they've got similar charges. Meaning things that have a negative charge don't want to be close to one another. So what do you think, Jake?
The first one.
The first one? So the first one, if we look at it, is it more or less stable? Yeah, what I would do is focus on charge right now. So if we look at charge, right, the first one we'd say this delta negative is in close proximity to that delta negative. That's pretty destabilizing as opposed to having them on opposite sides of the molecule, right? According to Vesper theory, we want to keep those partial negative charges as far apart from one another as possible. That actually means that the lower one is the more likely scenario. So this goes through the more stable transition state. And in fact, experimental evidence shows that we actually only get inversion. We don't observe any retention. Does that make sense? It's a little bit abstract to think about that transition state of making and breaking bonds, but it helps explain the stereochemistry, right? All right, so the main difference to focus on going back is up here we said you get a mixture of stereoisomers. We're down with SN2, you only get one product out. You don't end up with a mixture of two different products out of the reaction. Does that make sense? It's another experimental way of determining was the reaction SN1 or SN2. If it's SN1, you'd expect two products, but if it's SN2, you'd only expect one. So a simple trick to determine the difference. All right, so what I want you guys to do now is, I hope you guys all grabbed the flow chart up here. We're going to start filling in our decision making, because we've got enough right now to start working. And then we'll add to this kind of as we go through the chapter. All right, so how would we describe the mechanistic difference between SN1 and SN2? Who wants to help me with that? What was that? Well, let's just describe the mechanism. So how is the mechanism different? Let's leave the carbon until we talk about the electrophile. So think about, which one requires more steps than the other, I guess? SN1, right? So SN1, we said, is a stepwise reaction. And we said that the leaving group falls off first. In fact, that's our rate determining step, is that leaving group falling off, forming a carbocation. SN2 reactions, on the other hand, are concerted, meaning that it happens all in one step, right? And I like to describe this as the nucleophile shoves off the leaving group. So mechanistically, they're very different from one another in terms of whether or not they go through an intermediate or they don't. All right, rate equation. So we know that the rate for both of these is going to have some sort of rate constant, little k, so I'll write that down. For SN2, what concentrations matter? Yeah, the concentration of your nucleophile and the concentration of your electrophile. So I'm just going to write Nu for our nucleophile. And I'm going to write substrate, meaning the thing that it's attacking. So both of those components matter, right? Because it relies on the collision between two of them. All right, SN1, what concentration matters?
Leaving group.
Yeah, only the thing with the leaving group, right? So I'm just going to write substrate. It's a substrate with the leaving group, right? So occasionally in the book, they'll use substrate and electrophile interchangeably, right? All right, we just talked about stereochemistry. So for SN2, what's observed? Are we observing retention or inversion? Only inversion. So let's write that down. And we know that that's due to that transition state being more stable than the retention transition state. With SN1, what do we observe?
Both, but with a slight preference.
Yeah. Both inversion plus retention. But we know that there's a preference for inversion. So the main difference is with SN1 we get a mixture, with SN2 we only get one product out. All right, with SN2 we've got to look at the substrate or the electrophile. So what's the best electrophile for an SN2 reaction? Is it going to be primary, methyl, secondary? Which of the possible options is the best? Yeah, methyl we said is better than primary, which is better than secondary, which is way better than tertiary. So another way of saying this is sterics influences rate. So you want the least steric blocking groups attached. That way your nucleophile can get in and do its business. All right, SN1 we know is different. We said SN1 that tertiary is more stable than secondary, which is way more stable than a primary, which is way more stable than a methyl group. And why is this trend the case? It's not sterics anymore. What was that? Yeah, hybridization, or which carbon has the most hyperconjugation. We know tertiary carbocations are more stable than secondary and so on. So carbocation stability matters. All right, so these are the first 4 things we look at when we're analyzing these reactions, but we've got 3 more things we need to consider. We need to look at the nucleophile. So far I've just written NU as a generic NU, but there's a lot of different nucleophiles. We need to look at different types of leaving groups, and we need to assess the solvent for these reactions as well. So let's go back and take a look at nucleophiles, and then we'll fill in this chart as we go along. All right, so the nucleophile matters a lot for the SN2 reaction, but it also matters a little bit for SN1. So we'll talk about SN1 first. So I'm going to do 2 reactions and label them as A and B. Okay, for reaction A, I'm going to just have some generic leaving group. Whoop. And I'm going to have hydrogen sulfide as my nucleophile. Okay, if it's SN1, what's the first step? Leaving group jumps off. So our leaving group has a negative charge. We still have our sulfur around. Okay, as you can see, we've got a tertiary carbocation, which means this can do SN1. All right, in step 2, what do you think might happen? Yeah, sometimes students will ask me, well, the leaving group has a negative charge. Can the leaving group attack back in? It can, but then we're just going backwards, right? That doesn't get us anywhere. The only other nucleophile we have is the sulfur with the lone pairs. So that's actually going to attack in. Do we have to worry about a mixture of isomers here? Or stereoisomers, I should say? What do you guys think? Think about the carbon we just attacked. Is the carbon that we just attacked now a stereocenter? Do we have any stereocenters? No, so we don't need to worry about the mixture of stereoisomers in this example because there aren't any. Okay, so now we've got this. What do you think the last step will be in order to get to a neutral compound? Meaning right now our sulfur has a charge. We got to steal one of those protons back, right? The only thing that can steal a proton back at this point is our hypothetical leaving group. So it could deprotonate that. Now we've got this functional group with sulfur. What's that called? A thiol, right? So this would be our product. All right, let's do the same reaction, but this time with water. Just like before, the leaving group will fall off first. That's entirely the same. Now we've got our leaving group with a negative charge. We've got H2O still hanging around. We know that H2O can attack into that carbocation, just like the top one. Still have leaving group with a negative charge. We now have our water that formed a covalent bond, but it's got a positive charge, which means the last step of this reaction, again, will be that proton transfer. It's not unusual to see a proton transfer as your last step, especially for SN1 reactions. So now we've made an alcohol plus our leaving group that now has a covalent bond to hydrogen. All right. So now what I want to consider is which reaction is faster. What I want you guys to do is to talk with your neighbor and try to determine which reaction you think will occur at a faster rate and why. And just to give you a little bit of guidance, it could be a tie. So do you think A will be faster? Do you think B will be faster? Or do you think it's going to be the same? Toss a coin in the air.
50-50 chance.
All right, so let's go back. SN1 reactions, what's the rate equation? Yeah, okay, so the rate equation for SN1 is going to be our rate constant times the concentration of our substrate. What about the nucleophile? Do we include that?
No.
Okay, so let's go back and ask that same question now. Which reaction is faster? Assume the exact same concentrations. They're the same, right? Trick question. So let's make a note of that. The nucleophile does not affect the rate. Therefore, A and B are the same. It's a little bit weird to think about, but in this case, we did change our nucleophile from water to hydrogen sulfide. It doesn't matter, though, because that's not involved in the rate limiting step. Does that make sense? I tried to drill that in by tricking you guys. All right, let's do the next one. So SN2 reactions. All right, before we go on to SN2, let's go back and talk about this a little bit more. So SN1, we said the nucleophile does not affect the rate. Does that mean we should always pick a good nucleophile, or does it not really matter? It really doesn't matter that much. It doesn't influence the rate at all. So quite often with SN1 reactions, you see really weak nucleophiles because you don't need a strong one. A weak one's good enough to get by, right? The only thing that matters in these reactions is the stability of that carbocation. So weak nucleophiles are very common with SN1 reactions. In fact, you don't even need a nucleophile with a charge on it, which is nice. SN2 reactions, we know the nucleophile matters a lot more. So let's take a look at two different examples. And I'm going to use a primary substrate because we know primary substrates are more likely to undergo SN2. And I've got this nucleophile over here. And then let's compare this to reaction B. In reaction B, I'm going to have a leaving group. And then I'm still going to have a nucleophile. And what we need to do is provide reaction pushing arrows and the products for this reaction. So I'll give you guys a minute to work on that. And then once you think you have the reaction pushing arrows and your products correct, talk with your neighbor and see which reaction will occur more quickly, reaction A or B. Give me a thumbs up if you feel comfortable with the arrow pushing. Okay? So reaction 1, we know it's going to attack the backside of our electrophile and then kick off our leaving group all in one step. Same thing with this one. Backside, kick off our leaving group in one step. So our final product in this case is now going to look like that with two lone pairs and our leaving group. This looks familiar. What sort of functional group did we just make? An ether. In fact, this is diethyl ether, which is what you guys used in lab this week, right? This is called the Williamson ether synthesis and is a common way of making new ethers. All right, with the bottom one, it looks pretty similar. But now one side of the ether has a tert-butyl group on it, and the leaving group is entirely the same. What do you guys think? Do you think A will be faster, B will be faster, or do you think it'll be the same?
A.
You think A will be faster? Why do you think A will be faster?
start.
So what was that again?
It's sterically influenced, so it's less bulkier.
Yeah, so you're saying sterics, right? So sterics, I think, are a really good argument we could make. It relies on the collision of these two molecules. If one's really bulky, it's going to have a hard time orienting the right way to do that collision, right? So in this case, A is actually going to occur at the faster rate because the nucleophile isn't as bulky. So let's make a note of that. So A has a less bulky nucleophile. And the attack is therefore easier. That means that it's going to be faster in terms of the rate. So we know that sterics matter not only for that electrophile, but actually also for your nucleophile as well. With SN2 reactions, you want to minimize the steric interactions to encourage the collision of two different molecules. Does that make sense? It's a little bit weird to think about. There's also another example I want to show you guys. So example number 2. We're still going to do SN2 reactions. I'm going to have reaction A, and I'm going to have reaction B. For reaction A, we're going to keep the same substrate as reaction B, just like before. But this one, we're going to be using hydroxide. Down here, we'll use SH minus, so the sulfur analog to hydroxide. All right, so same thing. We want to provide reaction pushing arrows. We know this hydroxide as a nucleophile will do a backside attack, kick off our leaving group. Same thing with the lower one. And then down here, we'll do this. All right, so for argument's sake, let's assume that they're roughly the same size. They don't have that much bulk on them, right? They don't have a giant butyl group hanging off of them. Which of these do you think will be faster and why? So talk with your neighbor and see if you can convince them that you're right. Who feels pretty confident with their answer? Let's see a show of hands. How about anybody on the right side of the room? Nobody on the right side? I don't know if it's indifference or uncertainty. All right, so let's try to argue our way through this. Okay, if they're roughly the same size, we can't make a steric argument anymore. That means we're left with electronics, right? Electronically, which one do you think is going to be the more aggressive nucleophile? OH? Why OH?
It's more closer to the top right.
It's more closer to the top right. All right. So let's think about stability, right? Which is more stable, OH with the negative charge or SH with the negative charge? SH, right? Okay, so let's circle this and say more stable. Why is it more stable again? Yeah, larger atomic radius. Conversely, that means that this up here is going to be less stable because it's got the smaller atomic radius, right? So again, this is going back into some of those acid-base rules that we were talking about earlier. So if you're less stable, does that mean you're more or less reactive? More reactive, right? So reaction A is actually going to occur at a faster rate because it's got a less stable nucleophile. Okay, and I really like to explain this using a reaction coordinate diagram. So let's take a step back and draw that reaction coordinate diagram for A versus B up here. So we're going to have two reaction pathways overlaid on the same reaction coordinate diagram. Okay, so we've got Gibbs free energy over here. We've got reaction progress. Is it going to be one hump or two humps for these reactions? SN2 is always going to be one hump, right? Okay, so I'm going to just pick A up here. So I'm going to pick starting materials for A. We know it's going to have to go over some hump, and it's going to go to products, right? So if we look at this, we've got this one hump right here. What do we call that again? Activation energy. Okay, so activation energy for that one makes sense. And then we said, looking at the starting materials for B, they're more stable, right? So let's take a look at B down here, and I'm going to do B with a blue line. It's going to be lower in energy. So it's still going to have to overcome roughly the same amount of energetic hump. Oop. And it's still going to go to your products, right? But in this case, do you see how the activation energy for that blue pathway is a lot larger? It has the bigger hill to climb. So let's make a note of this. That activation energy for reaction A is lower, which increases the rate, since the starting materials are less stable. Does that make sense? So by bumping up the stability, we're actually lowering that activation energy at the exact same time. It's kind of an abstract thing to think about. Does that make sense? All right, so what I want us to do is go back to that chart that we have, and we're going to fill in the gap for nucleophiles really quick. So decision making. I'm going to close this. There we go. So nucleophile for SN1, we said doesn't really matter. Therefore, it's usually weak, which is a good thing. And then we said for SN2, we want two things. We want it not to be bulky. And then the second one was better if unstable. So for SN2, we really do care about the nucleophile, whereas for SN1, we don't. Does that make sense? All right, I think what we're going to do with the last 5 minutes is I want you guys to start working on the pod in class and try to talk with your neighbor about it. First thing you want to do is determine whether or not it's SN1 or SN2. And then what you want to do is provide the reaction pathway, determine whether or not you get one product or two products, and then name whichever products that come out of that reaction. Make sense? All right, and I'll float around the room too if you have any questions.